Modern artificial intelligence is an industrial powerhouse. Models today have hundreds of billions, even trillions of parameters. A single modern GPU consumes 700 watts of power, and training these models requires thousands of them. Meanwhile, the human brain, with more than 100 billion neurons and more than 200 trillion synapses, runs on about 20 watts, less power than a standard light bulb. How is the brain so unbelievably efficient? The secret lies in how they process information. Standard neural networks are dense. When you give them an input, they perform matrix multiplications across every single weight in the entire system. Your brain, however, doesn't fire every neuron for every thought. It routes information through highly specific neural pathways. Meanwhile, the vast majority of your brain is quietly resting. It's highly parallel and highly sparse. Before pruning, standard dense training propagates errors backwards to update weights. Researchers have tried to make AI sparse by pruning it, permanently cutting connections after training. This is called static sparsity. But what we really want is dynamic sparsity. We want a neural network to adaptively choose which fraction of its neurons to activate, rotate information purely based on the specific input it receives. But teaching a differentiable neural network to make discrete choices is mathematically tricky. To do it, we have to rethink the very geometry of how neural networks make decisions. Dynamic sparsity in neural networks often begin with a very familiar function, the rectifier linear unit, or ReLU. It is the simplest way to induce sparsity, pushing negative values exactly to zero. But instead of just thinking of it as a max operation, it helps to look at its variational form. Geometrically, ReLU is simply the Euclidean projection of a point onto the non-negative orthant. It's clean and it's fast, but it has a limitation. The outputs are non-negative, but they aren't normalized. They don't sum to one, so they can't be used as probabilities. When networks need to route information or compute attention, they need probabilities. The standard tool for this is softmax. It exponentiates and normalizes. But softmax has a fatal flaw. It is strictly positive. It never outputs true zero. In large models with long contexts, this causes the dispersion effect. The attention mechanism smears probability mass across thousands of irrelevant tokens, wasting memory and diluting focus. The extreme opposite is argmax, which outputs a strict one-hot vector. It is perfectly sparse, but it's fundamentally broken for training because it is discontinuous. Its gradients are zero everywhere. How do we fix this? One common engineering trick is top K softmax, heavily used in modern sparse mixtures of experts. The idea is simple. Compute the softmax, keep only the top K values, and renormalize the rest. It forced sparsity, yes, but it introduced two new problems. First, K is fixed, meaning the network can't dynamically choose which to attend to 3 things or 10 things at runtime. Second, like argmax, it introduced sharp discontinuities into our optimization landscape, disrupting the flow of gradients. Is there a way to get dynamic sparsities that is completely differentiable? Yes, enter sparsemax, or ntmax for short. The formula is simple. It is the max of the input z minus a dynamic threshold tau and zero, where tau is a dynamically calculated threshold value unique to that logic vector. To find tau, you must follow these 3 steps. First, sort the logics in descending order. Second, find the number of non-zero elements k by locating the largest index k that satisfies this condition. Finally, calculate tau using that specific k. Geometrically, we can compare it to softmax. As you can see, the sparse max surface is continuous and end-to-end differentiable. This makes it more efficient at cut-prop than softmax, while achieving true dynamic sparsity. In general, we can unify all three forms of softmax by using what's called an omega regularized argmax. For a convex function omega, we define the regularized argmax as the probability vector that maximizes the dot product of z and p, minus the regularization term omega of p. Argmax corresponds to no regularization, where omega is simply zero. Softmax amounts to entropic regularization, and sparsemax amounts to L2 regularization. We can generalize this further using Tersalis alpha negentrophies. The omega function is defined conditionally based on an alpha parameters. Let's look at how this parameter alpha changes the transformation. For alpha equals 1, we get the original softmax function. As we increase alpha, the distribution shifts, and at alpha equals 2, we get sparsemax. As alpha approaches infinity, we recover the strict argmax. So, where do we actually use these sparse transformations? First, sparse attention mechanism. By replacing softmax with alpha antmax in a transformer, attention heads can adaptively learn their own sparsity. The attention matrices become clean, improving both computational efficiency and explainability. Second, sparse losses. Using a framework called Fencher-Young losses, we can use these transformations at the very output layer of a language model. Instead of predicting a dense distribution over 50,000 words in a vocabulary, the model outputs a sparse distribution, assigning zero probability to bad predictions. This removes the need for post-hoc truncation tricks like top P or top K sampling during generation.